Welcome, everybody. Very excited to be here. So today we have a very special episode for you. Uh, the motivation really comes from many private discussions that I have had on topic of Bayesian modeling. Obviously, is what I've been doing a lot of, and how that relates to causal modeling, which is something that I personally have been exposed to much later. And it's always been a question for me: how do those really relate? And through many private discussions, sort of we gained many insights. And I thought it would be interesting to bring two actual experts on causal modeling, Alex Molak and Carlos Trujillo, with me, and then basically ask them to really get to the bottom of this. How do they relate? How do they benefit each other? Um, and yeah, so Alex and Carlos, thank you so much for joining. Maybe let's start with some introductions. Alex, do you want to start?
Sure. Thank you for the invitation, Thomas. I think that's a brilliant idea to have a conversation like this, because there's so much confusion sometimes on the internet, and when I see people discussing the intersection of these two topics. My name is Alex Molak. I'm a consultant and educator in Causality, Causal AI. I'm the author of Causal Inference in Python, Causal Inference and Discovery in Python. That's the full title. A practical book on causality, applied causality. And I help companies answer important questions, important business questions using different sets of causal methods. And my background is originally in analytical philosophy, psychology, and neuroscience. But for the last few years, I worked in machine learning and other different types of statistical and causal modeling. And I'm very happy to be here today.
Great, thank you. And Carlos, you're muted.
That's a good point. So thank you, Thomas. I'm very happy also to be here and be with you two guys. This is amazing. So my name is Carlos Trujillo. My background has been in marketing mostly, with a bit of machine learning. But in the most recent years, I have been going in this path of causality and Bayesian. So I would say that I'm a causal enthusiast, but that Bayesian by heart. So I'm doing now consultancy with PyMC and principal data scientist as well. There with Thomas. I'm also very excited to have these conversations and some questions.
Great. And I'm Thomas Wiecki. I'm the founder of PyMC Labs and one of the co-authors of PyMC. The Bayesian modeling package is also a causal modeling package. I guess that's one of the questions we're gonna try and answer today. Very very warm welcome to everyone that has joined us. We've really been pleased with all the interest and excitement for this. So I'm gonna launch a poll just to see where people are from, just to get to know a little bit, and we'll also have some other polls during the time. There's also a chat, but for like direct questions, it's actually better if you use the Q&A box. So in your window, you should have a Q&A thing, and that's where you can type your questions, and there they will stay until we get around to answering them. So yeah, and for any other questions, you can just put them in the chat. So yeah, I guess getting started, and with the main question that we set out to answer is Bayesian modeling, causal modeling, really, how are those two related? And maybe I'll start with my own sort of understanding, which definitely progressed over time. So very early on, I was like, okay, well, I guess they're like the same. We like have box and arrow diagrams that we do in Bayesian modeling, and then in causal modeling they have this as well. And asked many people, no one really seemed to be able to answer that. And then more recently, with talking to Carlos, I found that, like, well, it's a little bit more nuanced, where the way that I'm currently thinking about it, and that might change in the course of discussion, is that these happen largely at different levels of abstraction, where causal modeling is describing the high-level ways that your variables interact in a causal way, right? So we have A influencing B, and that says, well, there is a causal influence between them, right? So if I change A, I'm going to affect B in some way. But what that is not communicating is what is the actual nature of that causal effect, right? Like, is that additive? Is that multiplicative? Is that is that a linear effect, a nonlinear effect? So all these things. And then there is a Bayesian model, which can be causal and be an implementation of a causal graph. So the causal graph is more the abstract high-level representation that says, okay, well, in general, this is how these things are, but then we actually want to fit things to data concretely. Then we really need to be very explicit about our assumptions and the nature of these interactions. And then you can basically say, okay, well, and also just to start clarifying some terminology, which we'll use is there's the causal DAG, which is that causal graph of how these things interact. And then Bayesians, we talk about the data generative process, the DGP, which is related, right? But that is much more really the concrete implementation, how from certain influences was my data generated, right? And it's already in the name that this is like a data generation. So we have a simulator, right? Like when you have a Bayesian model, you can simulate new data. To the best of my understanding, you can't do that really from a causal model, right? That's just like, well, these things causally relate, but data is like sort of then later, and that's again where you need a concrete implementation. That can be frequentist, it can be Bayesian. So anyway, that's my current understanding, and that's what I'm going to use to kick things off and have other people maybe correct me. But yeah, kicking this over to Alex to maybe provide a little bit richer context around this.
Yeah, thank you, Thomas. I remember our conversation. We met some time ago for a recording for the Causal Bandits podcast, which is a podcast on causality that I also founded some time ago. And I remember we had a conversation on this topic, and I remember that when we met recently, earlier today, you told me how your understanding was also progressing, and that was very interesting, a very interesting thing to hear, because it roughly corresponds to how modern causal theory was also developed. So if some of you heard about a person called Judea Pearl, he's the godfather of modern causality, or at least modern computational causality. Pearl started thinking about how causal influence can be captured and how can we reason about causality. That was his question. He started with the idea of Bayesian networks. And I think that's very important also for us to lay a little bit of a ground before we go deeper. So what we mean by Bayesian modeling, right? So we often put different concepts that their names sound similar, like Bayesian networks and Bayesian inference, which is often Bayesian approximate inference. We put them together and we say like, oh, this is Bayesian modeling, right? But there are a couple of elements here. And so one of the very important elements that you mentioned, Thomas, is the structural element, how we build this model. So what PyMC is built about, the idea around which the PyMC library and ecosystem are built, is this idea that we build a structural model. And so sometimes we talk about those structural models with Bayesian inference as Bayesian modeling. Sometimes we say it's probabilistic programming. There are also different ecosystems, right, that also implement this idea. And so we have two ideas here. One is the idea about the structure, and this structure we intuitively, often practitioners in Bayesian modeling, defined broadly, will think about the structure in a way that is causal, because this is very intuitive for us. If we say, oh, we want to answer a question regarding how our promotions work. If we take all the variables and we are forced to structure them somehow, we will naturally gravitate towards a structure that causally makes sense for us, right? Because we humans are natural causal reasoners. And so we have this structural aspect, which is similar in what we refer to in the context of libraries like PyMC, ecosystems like PyMC. The structure is common to ecosystems like this and other ideas that appeared earlier in modeling history, like structural equation models and Bayesian networks. And Bayesian networks are not necessarily Bayesian from the inference point of view. We can do inference in many different styles over them. But what is important there is the idea of conditional probabilities, and hence the name, because the Bayes rule is related to conditional probabilities. So when we compute those probabilities over those networks, where nodes are different variables and edges are connections, which means there is some conditional probability this is greater than 0. Let's say, simplifying this a little bit, then there is an edge between two different variables. So the early idea with Bayesian networks was that we can capture, maybe we can reason about causes and effects in the world using just the structure of conditional probability and a Bayesian network. So that was one of the ideas that Pearl came up with in the 80s. But then he realized after, I think, 8, maybe on 9 years, that this is actually not sufficient. And so he developed the idea of a causal Bayesian network, where he said, oh, probabilities are not enough. We actually need a sense of direction. And that's, again, going back to what you mentioned, Thomas, in your intro, the structure and how the information flows in a network. So he said, we need the idea of direction, and this idea of direction not necessarily can be inferred from the data. We need to bring it from the outside. It's not a statistical quantity. Under certain assumptions, it can be, and that's what makes causal discovery possible. But in general, we cannot infer it without any additional assumptions. And then Pearl got very scared in the early 90s because he realized that actually causal reasoning requires us to go into even further. And this realization came to him when he realized that to talk about counterfactuals, which are one of the fundamental concepts for experimental causal inference, as introduced by Fisher, Neyman, and then Rubin, to talk about counterfactuals, we need something. We need something more, an even richer representation of a system. So it's not only about the connection between variables in terms that there is some dependence, statistical dependence between them. It's not only about adding a sense of direction. It's also about understanding those functional forms. So you mentioned this in the intro as well, Thomas. You said, "Oh, we put the meat on the skeleton, in a sense, right? We put a meaning into this model, into this scaffolding. We fill it with meaning, and the meaning is encoded by those functional dependencies. We say, oh, this is additive, this is multiplicative, this is maybe something else, and so on and so on. So the third layer, is called structural causal models, which means we have a graph, we have the structure, but we also have understanding of the functional assignments, how information from one node is being mapped to another node, right? So there's some function that is changing this information on the way. And those 3 levels, Bayesian networks, causal Bayesian networks, and then structural causal models, they also correspond to the 3 ranks of the ladder of causation that Judea Pearl has introduced some time ago. And it's a very powerful device to intuitively capture different levels of reasoning about causes and effects. The first one is association, the second one is interventions, and the third one is counterfactuals. And there's now a lot of great mathematical mathematical formalism behind this ladder of causation. So we can look at it from measure theoretic point of view, topographical point of view, and so on and so on. So that's when you told me your story, I thought that this is very interesting because it's so similar to how this theory of causality was developed.
Yeah, Yeah, thank you. That is really helpful historical and structural context. Carlos, I wonder what you think.
Yeah, no, I think that the first thing that I can pick from your speak, Alec, is like, as you mentioned, we usually tend to have this confusion between probabilistic programming and Bayesian approaches, and they not necessarily are like next to each other, and the same with structural models. And actually PyMC itself, if you go to the webpage, we say like, this is a library to do probabilistic programming. We never talk about the structural part, but I think that in a natural way, PyMC as a framework is causal because you are forced to give a structure, to give meaning to the Dags. And I think that that's something that not like people just usually maybe don't realize, right? When you start to create a PyMC model, you end up doing a lot of assumptions. You just do what you need in order to get your output. And in that way, you need to give a structure. You need to assume like, what is the direction of the data? What is the flow of this data? What type of nature this relation, like this equation, what should be the nature of this equation? And then when you get your result, even without knowing it, you did causal reasoning, you did a lot of causal thinking. And sometimes even you apply causal discovery steps in the middle, and you just don't know it. And I think that that's how, like, again, my reasoning right now, since I also start to go into causality, all of this came from marketing as well, just to put the dot. I think that marketing is one of these areas, and I think that Julia Per also mentioned it, where maybe we will adopt causality first, because we are facing not prediction problems like a lot of machine learning applications can face predictions, but in marketing, we usually want to attack decomposition. And if you want to decompose or have the model that can decompose the better, the real effects, the causal effects, then I think that it's very natural go in a causal way, even without knowing it. So it's I'm very happy to hear like all of this history from you, because I'm starting to think like, then at least PyMC, maybe not the Bayesian framework itself, but at least PyMC as an implementation of these probabilistic tools in the Bayesian framework is causal, because you cannot just go there to the final model without pass for these causal steps. It's like, you see someone driving a car and then you ask like, oh, do you drive? And he tells like, no, but wait, you're driving a car. How not? That cannot happen. So I'm very glad to hear that, and that we are going in that path. I don't know, Thomas, what's your take?
Yeah, I think you highlight something really critical, which is and that is also, I guess, had been my perspective also when talking to Alex on podcast. When looking at most of the models, for example, we build at PyMC Labs for customers, a lot of them are causal. At least there is like a causal way of understanding them. But like you say, Carlos, that causal element is like largely implicit, where like the model just sort of happens to be that. And then I thought like, well, okay, I mean, I guess then what new does really the causal framework add if that's already what we're doing? But Alex said, well, there's a couple of really important things. And one is, of course, the counterfactuals and interventions. And really like thinking about things from like like, for example, starting to be much more the importance of running experiments, right, to really identify certain nodes. But the other thing is also the communication, right? So, and this is something that we at Labs have struggled with since day one, basically, where it's like, okay, well, in different flavors. So one of them is when prospects ask us like, okay, well, what is so great about Bayes, right? And when you look online, like what's great about Bayes, it's like, well, it's uncertainty and it's priors. And then there's like some other things, but those are like the two biggest benefits. And I always struggled with that because, I mean, yeah, I guess that's kind of cool, but like, well, what if I don't really care that much about uncertainty? At the end of the day, right? Like a lot of people just still just use the point estimate. Priors, okay, I mean, that's sort of useful, but I don't know. Then there's this whole philosophical debate, and something you don't really want to get into. But really, now I think that the biggest benefit is that it allows you to build a structural causal model, implement a structural causal model, and really reason about your data and how your different variables fit together and what influences what, which is really, like you said, Alex, we're naturally causal thinkers, right? So this is already what companies, business stakeholders that maybe have never even done any stats are already thinking about, right? Like they think, well, these marketing things influence my sales in this way, right? And this is the direction of the causality, and these other factors that influence this, like seasonality and whatever. And then having the ability to communicate with them on that causal level really allows us to well, communicate the value, but also actually build the model, right? Because only staying at that Bayesian level, things are just like too detailed, right? It's like you write things down and it very quickly becomes a really complex thing with a lot of these formulas and whatnot, which obviously you need when you really implement it. But in order to communicate, well, what is actually underneath this? What is this really doing? You want some high-level abstraction that gives an intuition for what it is doing. And for that, I see a lot of value in that causal DAG. So rather than like blasting people with like the full statistical description of like the data generative process and talking about posteriors and priors, it's just like, well, okay, I mean, yeah, like when we really like break it down to its essentials, we have these 5 variables and this is how we think they interact. Then it clicks and people are like, oh yeah, cool. This is how I can now think about that and also argue about, right? Like maybe that causal DAG is not how the people thought about, but then that opens up the door to a discussion. Yeah, curious what has been your experience in using it in this way?
I'm really glad you brought it up. I think that this is an excellent point, and it really resonates or corroborates with what I've seen in my experience talking with people from different companies. So, you know, even when I talk sometimes to large multinational companies where they have like super complex supply chains, they have different departments that are not very well communicated between each other. It turns out that bringing a DAG to the table is a language that everybody understands suddenly. You know, they can get rid of their local dialects, so to say, right, that they use within their departments, and then can say, okay, this impacts this impacts that, I don't agree with this, I agree with that, and so on and so on. It also gives us a chance to leverage, you know, all those techniques that are very hot today, like large language models, to extract knowledge from a vast sets of documents that companies have, right? Of course, there are risks related to using large language models. I don't want to go into deep into this, but you can use large language models in order to do some kind of causal discovery on like a token level, let's say, rather than numerical variable level. And you can incorporate this into DAGs. You can also build the preliminary DAGs, and I think this is one of the ideas that I got from Ishan Gupta from BMW, that you can actually use a large language models to build a DAG for a given problem, maybe a supply chain problem or another problem, that is like an initial DAG. And now, so what I see and what I heard from other practitioners is that people were able to cut the time needed to build a in order to answer certain questions, right? In a traditional way, you have a lot of meetings where many people, many stakeholders are involved, and they need to communicate in order to establish what is the expert knowledge as of today. So this process, by using DAGs, can be cut by 50 to 70% in terms of time needed for this. I think in one of the companies, I heard that the process of building a DAG by using a large language model to generate the first initial DAG that is then criticized by stakeholders was cut by another 50%. So this can be, you can go to from 100% of time that is needed to collect the collective knowledge in order to start modeling something effectively, you know, to 25% of this of this initial time. I think this is a very powerful thing, especially in business settings where, you know, you usually want to save resources and you want to save time, you want to act fast, especially in these more competitive markets. So I think DAGs are a great language that can help us with communication, and it can also help in communication not only within a company, but also between people who are technical and people who are not technical. That's also sometimes a bottleneck, in my experience. So yeah, I think that's a really, really great point, Thomas, and I'm really glad you brought it up.
Yeah, and by the way, I'm absolutely really happy to hear that. I will say that by experience, I suffer the same thing, and was very gratifying when causality and Dags and everything appears in my life. Because let's say I remember like 5 years ago, I was doing, I don't know, media mix modeling for like Omnicom. It's like a very big marketing company, and then at that moment, you build your model, you have your equation, and then you usually say like, oh yeah, this is the equation behind my model, this is what's happening behind the scenes. And for sure, like your data science partners, they follow what you are saying and they could say okay or not. But all the other stakeholders that they maybe are like just pure marketers, or they are like, I don't know, CFO or CCO. And then they are like, well, I imagine that your equation is okay, like happy. But once you are able to actually bring the Dags and put everybody in a room, and that's why I feel that this is where I feel that Bayesian causality actually connects, because you put everybody in the room, and Bayesian gives you the tools to connect causality better, because again, everybody's in the room, not only saying, how do you believe that these nodes or different factors are connected between each other, but you can also put some prior knowledge on the strength of that relationship. And then in the Bayesian framework, you have the theory. I can take that information, make it a prior, and then finally go to my model. And I again love it, because at the beginning, the DAG looks like an hypothesis, right? Like you can think in a lot of DAGs from the same set of factors. You could have a lot of different combinations. And then the question is like, okay, which of these combinations, which of these DAG is actually true, right? You need to start to discover that part. And again, at least in PyMC, you could do it, because what usually happens is like when you have a DAG that is not true or is not actually following the real underlying structural causal model, then your final model, the thing that you get after your fit, it's like full of divergencies with very low sample sizes, with very bad R-hat. And then you have a lot of metrics that kind of tells you, okay, this structural DAG that I'm imagining and I'm trying to prove is not aligned to my evidence. So I think that again, one strong point of Bayesian and causality is that you can integrate this knowledge and you can make it part of your like causal discovery process. And you can actually do this, let's say, it's not a refutation test, it's not a falsification test, like as you could do in DoY or whatever, but it's very similar. You still will get some output that will say like, okay, this idea, this conception, this abstract representation of your data is actually not matching. And you have the way to prove it through the posterior, through the sampling. So I think that this is I don't know, something that I see, and I did it here at Wise. And by the way, I'm working also at Wise, and we have everybody in a room, everyone input their ideas, and we have like a few iterations where we quickly find out which is our DAG, and we could discard the versions of reality that actually were not true. Oh, this variable is not connected to this other node, or oh, we don't have a co-founder here because otherwise this should work, and so on. So I'm very, very happy to see that at least we have those tools in Bayesian. I don't know. What do you think, guys?
Yeah, I think it's very interesting. Thomas, go on, please.
No, go ahead.
Yeah, so I think that's very interesting. And I think you brought a couple of interesting points here, Carlos. So the first one is regarding testable implications, right? And I think it's very well said that a DAG is our hypothesis. That's exactly what it is. If you look at modern causal inference, and you look at the philosophy, the story of the philosophy of science, modern philosophy of science, right? We have this idea of falsification that comes from Karl Popper. And so what Popper says, simplifying this into 1 or 2 sentences, is that, okay, we have some observations. In some way, we built a theory, right, based on those observations. We say like, oh, maybe the sun is going around the earth because, you know, we feel we are still and the sun is moving and so on and so on. And so we build a theory like this, and then we generate some hypotheses, right? So a hypothesis from this, there's a number of hypotheses that we could generate from a theory that sun is moving around the earth. And well, it took us probably like 1,000, maybe more, maybe a couple of thousands of, a few thousands of years, to find actually evidence that was falsifying some of the hypotheses that were stemming from this theory. And so that led us to change the theory. So the theory is the structural causal model, basically, right? And then Dags are hypotheses regarding this, the causal structure. And so I think this is a very interesting perspective, and I think it's also a very important perspective when we think about evaluation of causal models. So that's one of the topics that I often discuss with people that with my clients, with people I teach, and so on and so on. How do you evaluate those models? Well, basically, we evaluate causal models as we would evaluate any other scientific hypothesis, right? We need to try to falsify it. There are different ways how we can try to falsify it. We can also use some maybe more formal methods that, you know, do not require us to go out to the world and perform an intervention. Sometimes we can narrow stuff down using different beautiful, smart techniques, creative techniques that we have. But basically what we're doing, we are trying to put stress on our hypothesis, as much stress as we can, and see if it still holds, right? And sometimes, you know, I feel like it's disappointing for some people, because maybe some of us, you know, we were taught, if we come from machine learning, we're taught that we have this validation set, and whatever the validation set says, you know, that's the reality. Of course, that's not true. That's very simplified. But in causality, some people have a feeling that they are missing the validation set, right? How I don't have a validation set for my DAG. What do I do with this? And there's some additional uncertainty perhaps here. Well, there's some explicit uncertainty that is implicit in traditional machine learning. That would be a correct way to say this. That makes some people feel a little bit maybe stressed about this this idea. But when we think about it a little bit more deeply, you know, causal modeling and the problem of evaluation of causal models, it just makes it explicit what we experience every day in our lives. We don't know stuff. All of us, we have hypotheses regarding reality, and we are sometimes forced to falsify our hypothesis, right? So when you think about, for instance, psychotherapy, psychotherapy is just like reworking your world models in a sense, right? We learned something maybe in the childhood or early adulthood, and it worked for us, but then it does not generalize to the overall world, right? So we go to a therapist, we talk to another person, and we discover our own world models. And we discover that some of our hypotheses are maybe not true, or maybe they are not adaptive for us at this stage. So there's certain there's some kind of special beauty for me when I think about the evaluation of causal models, because it's so close to, on one hand, to the heart, to the core of science, the scientific method, and on the other hand, very close to our everyday lives and all the challenges and struggles that we encounter in our lives.
Yeah,
So
totally. Sorry. I just want to say like that, that's basically what I love. And I said at the beginning, I'm Bayesian by heart. And that's why I like Bayesian and Causality, is because it's just the essence of science. Like that's how we actually do science. So it's just an extension of the scientific method, which, if you think about it, I mean, for me, it's like kind of beautiful. Like that's why I love to have this framework. Go, Thomas. Sorry.
Yeah, and beautifully said, Alex. I think it's worthwhile to then ask, okay, but why? like what really is the value of that, right? Like, so I think we established that it is more difficult, right? Like, what even is the validation set? How do we validate these causal things? Now we have to run experiments. Like, that seems like a lot of work. Like, why don't I just like fit black box machine learning model or just estimate some correlations? And well, I'm curious to hear your answer. My answer is that, well, if you only care about prediction, then that's totally cool, right? But if you actually want to achieve a certain outcome and you're working within a system that you can and want to affect in some way, then there's really no way around of having that causal understanding, right? One way or another, either like implicitly or explicitly. But yeah, if we want to know like how do we maximize sales given budget allocation of our marketing budget, right? Then we really need to understand exactly how these levers produce certain outputs, right? And then things like confounders become really important because they can fool you. And so, yeah, this idea of counterfactuals and it's important. And for counterfactuals, I think as well, that's where you tie in the need for a simulator, right? Because then you need to generate data for that alternative universe where you have an imagined intervention, and then you want to see, okay, what happened, what would have happened, or what will happen if I do this in my theoretical framework, right? And if that theoretical framework is incorrect, right, then of course you will get the incorrect one. So that's why it's important. But yeah, that it would be like my proposal for why even bother with that. I'm curious to hear what you think, Alex.
Yeah, that's a great point. And you started by saying it's more difficult, but I would say there's something very deeply humane in this. There's a saying, it's easy to live a difficult life and it's difficult to live an easy life. And when you think about it, when we have a causal question and we just put the data in some kind of machine learning model and we get some output and then make some decision based on some decision rule, because we need to remember that those models will not give us any answers to causal questions, right? We need to put some causal structure on them anyway. That's like an example of churn, for instance. People say, oh, if someone's churn probability is 0.75 or higher, then send the campaign or give a discount. So there's a decision rule on top of this that makes this model implicitly causal, right? But we don't put a work there that allows us to really answer a question that we are interested in. Now, we will, with very high probability, pay for this in the long run. So we don't put the work today, but we will need to put the work or pay the price later on. So some resources will go away from us anyway. So it's a matter of perspective. If we are ready to put the work today in order to minimize the cost and maximize the benefit in the future, or we just want to keep it easy now and then say, oh, maybe something will work out someday. So that's this. So in this sense, I understand your perspective, or like, the framing that you presented us with in the beginning, that it might be difficult. It might feel difficult today, but it's not necessarily more difficult in the long run in terms of the resources that we will need to devote. We'll need to, burn, so to say, right, in both cases. It's just a matter of taking a perspective. And, I think that's very humane, right? If you look at, I don't know, people who are into fitness, right? And people who want to lose weight by taking a pill, it's the same. It's basically the same mechanism, right? We value what we have now more than some perhaps more uncertain benefit in the future. Yeah. So yeah, I'm really glad you brought up this perspective.
Great. Okay. So yeah, go ahead. And after that, I want to make sure we have enough time for the Q&A. Carlos.
No, I just wanted to say, like, that time that you are like saving today to take the easy thing, at least in industries like marketing, is still like trillions of dollars. Like we're talking about like, you know, companies in marketing can spend billions on their advertising. So that I would say that easy way ends up maybe being as well the more expensive thing to do. That even if you just do everything at the beginning. So yeah, I'm like, just want to say that I'm super agree. You nail it with that point, Alex.
Yeah, it's very interesting. You know, like look at Booking.com, for instance. They are like a multi-billion dollars company, right? And their culture is so deeply causal that you would not believe that. These guys are A/B testing bug fixes in their code base.
Yeah.
You understand? They run A/B tests on bug fixes on their code base because before they push to production, they run an A/B test on like a smaller subset. They do like the recommender systems are based on causal machine learning models wrapped in some optimization schemes and so on. That's work from, for instance, Dima Goldenberg, who was also a guest of in my podcast. So you know those companies, they really understand that putting this work now in order to really answer the questions that are interesting to them, it's just beneficial for them. They understand this very well, and the same is true for companies like Spotify, like Netflix, and so on and so
on. So let's do some Q&A. So the first one was actually whether there was like a graphic. So usually we have like slides, but this is a different one. But there was one thing, one graphic that I recently created. Actually, it's the wrong one. That I recently created that for me at least is communicating this loop that we talked about. Does that okay? Where there are business stakeholders with their own domain knowledge, objectives, some key variables that they're interested in, and they already like have either implicitly in their head, right? But like you can ask them to create this causal DAG, provide insight, define goals, identify relationships, and then here I put PyMC Labs team, but it's just like the data scientist, right? The causal modeler that can take this causal DAG model and formalize that into like a Bayesian model, the actual implementation, right? This is what we talked about in the beginning, how these two things relate together. So here have the high level abstract representation, how these things fit together, and then that can give rise to a Bayesian model that is the actual implementation. And of course, there's then also this feedback loop, right? Where like from this work and the insights and the data and seeing where maybe it mismatches the data, right? Where you can falsify certain things, then update the causal DAG. So this is like, yeah, just I thought this might help put some structure on this workflow and still early days, but this is how I think this whole thing well, is working for us and can work in general. And then here's just an example of how that causal DAG can look like in the case of marketing, where we have performance marketing spend, and these dotted lines are ones things that we can control, right? So we control this, that influences sales, and this is oftentimes where MMM modeling would just end. But then you can imagine just adding more things in, right? Like things become pretty free and flexible at that point where, well, the price influences our sales, as does the price of the competition, which we don't have control over. And then there's this other branch here where we have consideration of whether to buy a product, right? So more the actual purchase process, which is driven by interest in your product and awareness around the product, right? Do I even know about this? Which is at the level where brand marketing is operating, and there's like other things like demand, right? So obviously you get the idea, but this is just one example to make it really concrete of the type of ideas that we're talking about. And then, of course, you take this this causal DAG, and then you could implement this in, for example, PyMC marketing. And this is definitely the direction that we're taking. So that was the first one. And then, well, let's just start at the top. So Sarah asks, how can any causality approach estimate the effect of a media channel on a target variable with just the given data set and not realize data for a non-treatment case? For example, how can it calculate the effect of TV spending on sales over a given time frame and answer questions like, what would have happened if we didn't do TV at all? What if we had doubled the TV spendings? Can you recommend a causality approach package to do things like this with a classic media mix modeling dataset? The approaches I found always work for treatment, non-treatment group approach, but not for time series data and multiple media channels.
So yeah, I would like to give just one sentence here, that when we talk about causality, we will sometimes hear questions like, oh, which package should I use to address a certain problem, right? And this is a very natural approach when we think about any applied work. We'd like to know what is the tool that allows us to answer certain questions. And I think one challenge that it's never you cannot overestimate how often we should probably repeat this, is that with causality we have this idea of causal identification, right? And so this means that we need to observe, we need to understand the causal structure in the process, and we need to observe certain variables that we have in our DAG, assuming this DAG is a good representation of the reality, in order to identify causal queries or causal quantities. Now, in probabilistic programming framework, it's, in a sense, maybe in certain cases it might be easier because we just put everything. We need to put the structure on everything, and even if we have a collider or something like this, it will not impact negatively our estimates. In the framework that does not use the structure explicitly, like we do it in DoI, for instance, or like, sorry, in DoI, probably the package would tell you as well that you should not observe this variable. But if we do it like just put something into a machine learning model, then we can get into trouble, right? If we put certain variables. So I think this is important to emphasize that sometimes, always when we think about causality, it's important to remember that we need this idea of causal identification if we want our results to really answer our questions in an unbiased way. And I understand that that was just like a little part of the question. So I'm very happy to pass it to you, Thomas or Carlos, to take the other part.
Yeah, I think you said it well. I did post a link to a blog post that we wrote on that topic. If you go to the PyMC Labs website, there's a blog post on causal analysis of PyMC answering what if with the new do operator, where we show how to do that. Technically, obviously, it rests on the assumptions that causal graph is correct, right? So and there you have lift tests, which are experiments, and other validation steps. So it's at that point you your own sort of marketing scientist. But then, yeah, you can implement these quite easily with the tools, and PyMC Marketing, I think, also supports these counterfactuals. Yeah, Carlos, do you have anything to add?
No, I just wanted to, I think just to add maybe a bit more of meat to the grill is like, as Alec was mentioning, you have a lot of like also graph theory about which variables you should control in order to identify the effect of another variable. So in this case where you have like TV, you could also, like, again, doing the assumption that your DAG is right, you could control for those variables which you need to identify in order to block what we call the backdoor path and identify correctly this node that you're interested in. And that node, in theory, if your DAG is right, should not get like, you will get this fair estimate that for sure you want to ratify with experiment, but that doesn't mean that just doing the regression, you will not identify the effect correctly if you follow or if you block for backdoor path. So again, experiments is the way to measure it out of the box, but that doesn't mean that your initial estimate will be wrong. I don't know if you agree, Alex, as well.
Yeah,
go
on, Thomas,
please. Yeah, if you have something quick, but I want to make sure we get through some other questions. There are quite a few, but go ahead.
No, I just wanted, I didn't have anything important to say, so please, yeah, I don't want to lose our time.
So Robson asked, in the Bayesian approach, how does one typically assume these structures, and how can we validate that this assumed Dags structure reflects the true unseen relationship in the data, given that it's not directly testable? As context, I'm more familiar with methods like differences, instrumental variables, and regression discontinuity design, which are relatively agnostic about the underlying structure of relationships and provide indirect ways to test their assumptions. I guess, yeah. Validation of the causal structure, which I think we discussed quite a bit, but yeah, I don't know, Alex, maybe you want to provide like 1 or 2 pointers.
Yeah, I think maybe one important thing is what we discussed before. So we will often have some testable assumptions. Now, again, the fact that our model has survived some attempts to falsify it doesn't mean it's a true model. It just means this model has good enough correspondence to reality that we fail to falsify it, right? And this is also the case with any scientific theory. When you think about, I don't know, physics, right, classical mechanics, and then relativity, the relativity theory, and the quantum mechanics, you know, all those theories were pretty good, and they were very, very robust against the different attempts for falsification. But it turned out that there is a better theory because we can actually falsify this theory at some point. We did some experiment or some thought experiment, and we're able to see a little crack in the theory. So it's the same with causal models. This is how we do it. And what Thomas mentioned before, experiments are really a really great way to try to falsify claims that we encode in our Dags, so to say. Experiments can help us if we understand the conditional dependence stuff. We can also use experiments in a way that is a little bit more efficient, right? So we can run an experiment on 2 variables, and maybe we can actually try to falsify 3, 4, 5 different edges by just running one experiment if we nail it down nice in the structure. Now, going back to difference in differences and synthetic control and so on, I think it's also important to remember that these methods do not give us causal identification out of the box. So we are still susceptible to hidden confounding, to selection bias potentially, and so on when we are using this method. So even though they look very intuitively, so with synthetic control, you know, we just look at the graph and we just compute the area between the curves, and it looks like it gives us a causal effect just out of the box. It's unfortunately not true. So we can use also causal graphs with synthetic control and other quasi-experimental designs. And there's a great paper by Kieran Gilligan-Lee from Spotify and colleagues who wrote about this. And we will have a special episode, by the way, of the podcast with Kieran next week during the causal data science meeting, where Carlos will also be presenting, I believe. So feel free to join us next week to learn more about this. We'll be discussing his paper. So just to wrap it up, you know, we can only try to falsify our claims. And unfortunately, the methods that sometimes give us impression that they are not susceptible to potential biases coming from confounding and so on, they also are susceptible to those biases. So this causal structure is important, and it's our job to think about effective ways to try to falsify our own assumptions.
Next question, I'll turn to Carlos. Can you help me better understand the difference between machine learning prediction and causality in the context of marketing measurement, specifically media mix models? the two seem similar to me in that you're trying to answer the question, how much did campaign A drive sales? You're muted.
Sorry. I will say that in the general context or in my experience, when I start to do media mix modeling from a more machine learning approach, you are usually just building your model, not thinking so much around these causal relationships, and then getting a final estimate of your target variable, right? And you usually have actually, and this is something very important that I want to mention, is like, we spend a lot of time evaluating the final answer of, let's say, our ecosystem, of our DAG around the target variable. And sometimes the fact that we have a model that fits well or have a low MAPE or similar is not correlated to the fact that we are getting the right causal signals. So if you're in the machine learning approach and then you're just doing the SMMN and you're evaluating only because it's fitting good, even in sample or out of sample, that this can happen. You can have a very good out of sample performance even when the true causal signals are wrong. That doesn't mean that you are getting the true causal signal of a specific node. And this is easily like falsified, because you can then do a test, and this is what usually happens, is like you start to take decisions on that specific node, and then the final estimation start to fail. So and we will explain this in causal data science meeting with Ben, that is also joining from the PyMC Labs team. But when you have these models that have all the coefficients like incorrectly, you could do a prediction moving all the nodes together, and still the final outcome, the overall, will be okay. So you predict, you move all the nodes, and then still the final prediction looks quite close to reality. And this is because you have, like, to put it in a way, you have a lot of different ways to zoom 10. But once you are playing with a single node, and you condition that node to have a value, and then you say, okay, all the other nodes will remain the same, and I will only move, let's say, Facebook, and then you move it, and then you compare to reality, then you will see that that's basically off. So I think that's basically the difference. When we are applying this causal thinking, this causal reasoning, we are not only interested in how a model is representing the whole ecosystem, we are actually interested in how each node of this model, each component of the model it's finding the real causal signal. And that's something that you could test through experimentation. And that's basically what, by the end of the day, you want to understand. You don't want to predict goods like sales good. For that, you have a lot of different ways to do good, very nice predictions. We want to decompose. I think that I mentioned this at the beginning. Like in media mix model, this is a decomposition problem, not a prediction problem where we want to measure accuracy.
Yeah, that's a great point. And I think that's also worth emphasizing, that we can get very, very good fit metrics like R-squareds and whatever you think about, right? The Bayesian information criterion, whatever metrics, fit metrics we are using, we can get excellent fit metrics. And then we move we move out of the distribution, right out of the distribution of treatment that we had in our training data, and the model collapses. So that's why this is so powerful to run randomized experiments, as Thomas mentioned before, because this allows us to falsify certain claims, sometimes in advance or post hoc, whatever works for our case, and it helps us avoid situations like this.
Yeah. Wasting millions of dollars.
Yeah, sometimes it's literally exactly this. Yeah.
So officially we are time. Personally, I'm okay to go a couple of minutes earlier. Is that okay with both of you?
It's okay for me. I can stay 5 minutes longer. Yeah.
And for anyone joining, we won't be offended if you drop off. So, but yeah, just there have been some great questions, and we'll just give it a couple more minutes. So one of them is, a lot of the focus in DAG building is on the nodes, the variables, but the edges, functional relationships, are just as important. One power of PyMC and Bayesian probabilistic programming in general is to be able to flexibly estimate any functional relationship without needing to do any special tricks to, for example, render it as a special case of some estimator. So it's not a question, but like it really encapsulates perfectly, really, well, how I think about it and a lot of the discussion that has been going on. causal Dags are great at, these are the nodes, these are directions of how information causality flows. But then how is that functional relationship? It doesn't really make any statements about that, but it is extremely important. And the Bayesian framework in PyMC requires you to do that. And yeah, that's where it's implementation. And I guess, yeah, one of my overarching points is that I think the best Bayesian models are causal, and the best causal models have a Bayesian implementation. So I think the two really like go hand in hand, and the Venn diagram overlap has a really good sweet spot in between. Can build a frequentist model, but it does have issues, and there's another question with that. But yeah, it gives you all that flexibility. It gives you the uncertainty estimate, right? Like how good do I even think these functional relationships are? How strong are they? And of course also the priors.
Yeah, so if I can add one comment on top of this, I think it's very important to remember that, you know, it's causality is not a synonym for a DAG, right? Or the other way around. We have those different ladders, the different ranks of the ladder, and so DAG is only a structure. It's only the structural information. If we want to answer certain queries, we won't be able to answer all the queries just with a DAG. We need a richer specification, for instance, to identify counterfactual queries, right? So we need to move to the structural causal models, which is related to what you are saying. We need to understand the functional assignments between the variables. And as you said, I think, you know, we can build structural models in different ways, in different flavors. We can use we can put Bayesian inference on top of this. We can use priors and posteriors and so on. We can do it in a frequentist way as well, right? I know in DOI GCM package we can do it. And that said, I think if you really want to do something on like a production level, probably probabilistic programming languages are the most mature tool on the market. And, you know, there might be certain advantages to be able to incorporate prior knowledge, for instance, especially in smaller sample sizes, right? There are certain probably also advantages to going frequentist, right? Maybe you want different estimates of uncertainty using like conformal prediction or something like this. Because maybe you care about the frequentist coverage in your case, which might be very important in certain cases, less important in certain other cases. So there are many ways we can operationalize it. Probably the probabilistic programming frameworks like PyMC, like Cairo or Pyro are probably the most mature frameworks that we can find on the market today. I don't know if you would agree with this. I would be very curious to hear your perspective. I know that you are also involved in PyMC, right? So
yeah, I completely agree, maybe not surprisingly. And I think that is something that is not as obvious to a lot of people, which is part of the reason for this webinar, is that if you obviously if you come from the Bayesian direction, right, and you think that Bayes is cool, well then very quickly you will start using Stan or PyMC or any of these other packages. If you come from the causal direction and you read Pearl's book, then you're like, okay, well, what are the causal packages out there? And then you find DoY and other things, and they are great packages. But in terms of really that detailed modeling and the actual implementation, and then being able to do these factuals and functional relationships, like everything we talk about, right? And that coupled with like the maturity of these packages, that's when really I think you're in the domain of probabilistic programming packages like Pyro, NumPyro, PyMC, where they really shine. Carlos, there was a question for you that you wanted to answer.
Sure. So basically, the question is, we were talking about like these divergencies for our hard or low effective sample size respect when we assume these wrong causal relationships. Just to deep dive, once you assume a DAG and then that DAG you represented with some structural causal model based on some structural causal equation, and that's wrong, usually that tends to create, again, your knowledge or your prior knowledge and your evidence don't align. And that just results in a model that gets a lot of divergencies in a PyMC model that ends up with a lot of divergencies or very low sample size or very bad fit in a lot of different ways. So what I want to say is like a lot of people tend to just evaluate even Bayesian models only based on the fit, sometimes even based on the level of uncertainty or the standard deviation of your posteriors, which is okay, but the sample process also gives you a lot of information to understand if your evidence and this assumption of your structural equation are aligned, are connected. So if you start to see, for example, these three values, you can quickly see when a parameter is like wrongly estimated or poorly estimated. And that basically could represent that maybe your structural causal model behind it is not correct. I usually, as Alec was mentioning, for example, I think that this match between do-y and PyMC, it's also like very nice. You can just take a DAG that you imagine, pass it through do-y, falsify it. You can run a lot of refutation tests on it, and then understand if that DAG somehow represents better than reality than a lot of others. I really like they have this example where basically you permutate your DAG, you generate a lot of random DAGs, and you see if the one that you are providing is better of all of these permutations in a way. And please, Alec, just jump if I go in the wrong way at some point. But that quickly can tell you if your initial assumption is wrong. And then if it's wrong, then you basically just need to move to another graphical representation that you can finally implement in PyMC. And that's it. So you start this, again, scientific method iteration. So you get your DAG, you falsify it with do-y, you move it to PyMC, you see if in PyMC it works. And based on that, you go again, you go into the loop again. One thing, by the way, spoiler alert, that we are trying to implement in PyMC is this opportunity to take a graphical model and then automatically create a PyMC model from it. So hopefully in the future, you could do something like, I don't know, PyMC marketing or PM, whatever, build model from that, you pass your graphical model, and then you get a final PyMC model implementation, which you can evaluate and get more of these like do-y features. But right now, if you want to just do it in that way, I think that with do-y is an amazing tool to apply it.
Great. Well, I think in the interest of time, we'll leave it there. Apologies if we didn't get to your question. Where there's like many different avenues to well, get in touch with me or Carlos or Alex in communities. There's the PyMC discourse, and you can check out PyMC Labs, pymclabs.com, where you find information of how to contact us. Also on Twitter. I'm personally on Wiecki. But yeah, that's it from me. Carlos, how do people best find you?
Same. You can reach me by LinkedIn, also like Twitter. I'm a bit active there, so yeah, I will leave my links on the bio of the video by the end of the recording.
And Alex?
Yeah, I left a link in the chat now for those who want to reach out. So there's a page where you can find my social media and other stuff. And well, I see there are still some excellent questions in the Q&A. I'm really sad we cannot address them, but please feel free to reach out to any of us, and I'll be happy to answer them.
Great.
I'm sure Thomas and Carlos as well.
Well, thank you both so much. Thank you so much for the attendees, for the many questions, for tuning in, for being interested in these concepts and being a part of the community. And yeah, we hope that what that was interesting. I certainly learned a lot. So thanks, everyone.
Thank you, Thomas. Thank you. Thank you
Thanks
so
so
much. Thank you, Carlos.
Bye-bye.
Bye.
Bye-bye.